Welcome to this course on probability and statistics. This is an introductory course, or you can say a first course on the probability and statistics, and it is quite useful for all branches of science and engineering. So, to begin with, we introduce algebra of sets. This is required because the modern theory of probability is based on the set theory. So, here we introduce certain elementary concepts of sets, which will be directly used in our definition and concepts of probability. So, to begin with, we start the discussion on what is set, classes and collections. So, we have start with a universal set, let us call it omega, and then we also have the usual notation for the empty set as phi. We call a set of sets to be the class and a set of classes to be a collection. As an example, consider suppose omega is the real line R, and we consider the collection of intervals starting from a to b, where b is greater than a for every real number a. Then this C A is a class of sets for each a, and then if we collect all these classes C A into a set called script E, then this is a collection. For any two sets A and B, which are subsets of omega, let us consider the relation A related to B if A is a subset of B. Then the relation R is reflexive and transitive. It is symmetric when omega is equal to phi. We introduce some further conventions and notations. If the index set I is empty, we make the convention that union of EI's is empty, and also intersection of EI's is the full set omega. The second of this convention looks to be rather surprising. However, it is motivated by the fact that if we take more and more sets in an intersection, then it becomes smaller. For example, if I have two index sets I1 and I2, such that I1 is a subset of I2, then intersection of EI, where I belongs to I1, contains intersection of EI where I belongs to I2, primarily because the more sets means the intersection becomes smaller. Hence, the smallest possible index set, that is phi, should lead to the largest intersection, that is omega. This convention is also consistent with De Morgan's laws. For example, if I write union of EI, I belongs to I, complement is equal to intersection EI, complement I belonging to I. Let us take I to be phi, then the left hand side is equal to phi, complement is equal to x. This indicates that we should take intersection of EI when I is an empty index set, then this should be equal to the full space omega. Let us introduce the concept of indicator function or characteristic function. The characteristic function of a set E is defined to be 1 if x belongs to E, and it is 0 if x does not belong to E. Alternatively, we can write the set E as the set of all those points for which x chi E x is equal to 1. Clearly, indicator function of the empty set is always 0, and the indicator function of the whole space is always 1. There are certain exercises here. For example, if a set A is a subset of B, then the indicator function of A is always less than or equal to the indicator function of B. Conversely, if the indicator function of the set A is always less than or equal to the indicator function of B, then A is a subset of B. A simple proof of this is that if we consider chi A x, then it is equal to 1 for all x belonging to A. And since A is a subset of B, this implies that chi B x is also 1 for these points. Now, for the points where chi A x is equal to 0, include certain points where chi B x may be 1, and for all other points chi B x will also be 0. Therefore, chi A x is always less than or equal to chi B x. We have certain elementary properties of the characteristic functions. For example, characteristic function of an intersection is equal to the product of the characteristic functions of the two sets. It is also equal to the minimum of the indicator function values for those two sets. The proof can be simply obtained by definition. For example, chi of E intersection f x is equal to 1 if x belongs to both E and f and 0 otherwise. That means it is going to be equal to 1 only if chi E x and chi f x both are 1, and in every other case it is going to be 0. So, that means it is equal to the product. In a similar way, the minimum of chi E x and chi f x is going to be 1 only if both chi E and chi f x are 1. That means chi E intersection f x is equal to 1. Similarly, the indicator function relations for the unions, complementations and differences are also there. For example, chi of E union f x is equal to chi E x plus chi f x minus chi of E intersection f x. It is also alternatively equal to the maximum of chi E x and chi of f of x. Once again, to look at the proof of this, we can see that if we write maximum of chi E x and chi f x to be say 0, then both of chi E x and chi f x must be 0. Hence, chi of E union f x will be equal to 0. If maximum value is 1, then either 1 or both of chi E and chi f must be 1, and so chi of E union f will also be 1. The other properties of chi function, for example, chi of E complement is equal to 1 minus chi E, chi of E minus f is equal to chi of E intersection f complement x, which is chi of E into chi of f complement from the property 2, and chi of f complement from the above property is equal to 1 minus chi f x. So, these are some of the useful relationships for the indicator function. We have all heard about the limit of sequence of numbers. For example, you easily understand that limit of a n is equal to a if for every epsilon greater than 0 there exists capital N such that modulus of a n minus a becomes less than epsilon whenever n is greater than or equal to capital N. This shows that the sequence a n is closer to the number a, the values of the sequence a n become closer to the number a as n becomes large. However, the similar concept is not available for the sequence of sets. Here we define it in a slightly different fashion. So, in order to introduce the concept, we introduce the concept of lim sup of E n and lim inf of E n, are called limit superior of E n or limit inferior of the sequence E n. So, consider a sequence of subsets of omega called E n, we define E upper star is equal to lim sup of E n, which is equal to the set of all those points which belong to infinitely many values of n. What does it mean? It means that from the whole space we take up those points which belong to E n for infinitely many values of n. The collection of such elements will be called limit superior of E n. In a similar way, we define limit inferior of E n called E lower star. It is the collection of those elements of omega which belong to all except maybe a finite number of values of n. That means they belong to almost all the values of E n except maybe for a few of them. If E upper star and E lower star are the same sets, then the common value is called the limit of E n, and we say that the limit of the sequence of sets exists. By the definition, it is clear that in general we will have E lower star as a subset of E upper star, primarily because if x belongs to E lower star, then already we are committing that it is belonging to infinitely many values of n, because it is belonging to all except a finite number. That means definitely it is belonging to infinitely many values of n. Therefore, in general E lower star is always a subset of E upper star. When it is equal, we say that the limit exists. Let us consider some simple examples of application of the concept of the limit of sequence of sets. Consider, for example, E n set defined to be an open interval 0 to 1 minus 1 by n for n is equal to 1, 2 and so on. Here if we calculate the limit inferior, then if you consider any point in the interval 0 to 1, then since 1 by n goes to 0 as n tends to infinity, for every number a between 0 to 1, we can find for every 0 less than 1, we can find capital N such that a is less than 1 minus 1 by n for all n greater than or equal to n. This shows that a will belong to the interval, a will belong to E lower star. This also shows that a will belong to E upper star. So, E lower star is equal to E upper star is equal to the interval 0 to 1. So, this is a case where the limit exists. Let us take another example, the sequence of closed intervals from 1 by n to 1 minus 1 by n for n is equal to 2, 3 and so on. Once again, if we utilize the argument as given in the example 1, if we consider any element a between 0 to 1, then after a certain stage it will belong to the set E n for all n greater than or equal to some capital N. Therefore, once again the E lower star, that is the limit infimum of this sequence, will be the interval 0 to 1, and naturally E upper star will also be 0 to 1 because it is a superset of E star in general and it cannot be go beyond the interval 0 to 1. Notice that here the point 0 itself and the point 1 itself do not belong to E lower star or E upper star, because for no value of n these points belong to the set. Now, I will give one example where the set E n is defined in a has a finite number of points, and here E lower star and E upper star are different. Consider the set E n given by 0, 1 by n, 2 by n, n minus 1 by n to 1 for n is equal to 1, 2 and so on. Then if this particular sequence can be explained like that, if we consider E1, then it is the set 0 to 1. If we consider E2, then it is the set 0, 1 by 2, 1. If we consider the set E3, then it is equal to 0, 1 by 3, 2 by 3, 1. Clearly, the points 0 and 1 belong to all the sets. Therefore, E lower star, that is the limit infimum, must contain the points 0, 1. Now, we say that no other element of the form, say P by Q, can belong to all the sets E n's even after a certain stage. For example, the point half, it will belong to once again E4 because 2 by 4 will come, it will belong to E6 because 3 by 6 will come. So, it will belong to infinitely many sets, but it will not belong to all but finitely many. Similarly, if I consider say 1 by 3, then it will be there in E3, it will be there in E6 as 2 by 6, it will be there in E9 as 3 by 9, etc. So, it will once again belong to infinitely many sets, but it will not belong to all but finitely many. Suppose we consider a point say 2 by 3, then it is belonging to E3, then it will again belong to E6 as 4 by 6, it will again belong to say 9 as 6 by 9, etc. Therefore, we conclude that all the rational numbers in the interval 0 to 1, all the rational numbers of the form P by Q in the interval 0 to 1 will belong to infinitely many of the E n's. Therefore, E upper star will be the set of all those rationals in the interval 0 to 1, whereas the limit inferior is equal to the interval and the set consisting of the points 0 and 1. Another example is we consider the sequence as split into two parts, that for even ordered sets E n is one particular set say A and it is equal to B for n odd. Then E lower star is the set of points which are common to both A and B, because if we consider a point which belongs to both of them, then for all but finitely many sets of E n, x will belong to them. However, if a point is not in one of A and B, then for infinitely many values of n it will not belong. Therefore, the only points which can belong to E lower star are which are common to both A and B. On the other hand, any point which is belonging to either A or B will be there in infinitely many sets, and therefore, the E upper star will be A union B. Naturally, you can see that E lower star is equal to E upper star if and only if A is equal to B. Let us consider a disjoint sequence of sets. If we apply the definition of limit superior and limit inferior, then we note that there are no elements of omega which belong to two sets, because the sets are disjoint. Therefore, no point in the set omega can satisfy the property of belonging to either infinitely many ENs or all but finitely many points of En. Therefore, limit inferior as well as the limit superior both are the empty set, and it is equal to limit of the sequence of the sets. In order to derive the limit inferior and limit superior using mathematical arguments, one may look for the alternative representations for these sets. For example, limit inferior can be written as union intersection En, n is equal to m to infinity and m is equal to 1 to infinity. In a similar way, limit superior can be written as intersection union of En, n is equal to m to infinity, m is equal to 1 to infinity. To prove these statements, let us take the first case. Consider a point x belonging to limit inferior of En. By definition of the limit inferior, it implies that x belongs to En for all but finitely many values of n. This implies that from a given m onwards, x will belong to all the sets En. That means, x will belong to the intersection of En, n is equal to m to infinity for some m is equal to 1 to etc. Clearly, this implies that x belongs to union intersection En, n is equal to m to infinity and m is equal to 1 to infinity. On the other hand, if we take x belonging to union m is equal to 1 to infinity intersection n is equal to m to infinity En, then this statement implies that x belongs to intersection of En for some m is equal to 1 2 etc. Now, this statement once again implies that x belongs to En for all but finitely many values of n, which was actually the definition of limit inferior. Therefore, we have both way implication for all the statements, and this proves that limit inferior of En is equal to union intersection En, n is equal to m to infinity, m is equal to 1 to infinity. If we apply the same argument for the limit superior, then we get that if x belongs to intersection union En, n is equal to m to infinity, m is equal to 1 to infinity. So, I am taking the right hand side first. Now, this implies that x belongs to union En, n is equal to m to infinity for every m is equal to 1 2 etc. Now, if we say that x belongs to the union starting from every m, howsoever m large may be, this definitely implies that x belongs to infinitely many values of n, because if it was belonging to a finitely many values only, then after a certain stage x will not belong to the union of En's. However, it is belonging for every value of m. This means that x belongs to En for infinitely many values of n. which is actually the definition of limit superior. Now, to look at the argument in the reverse way, if x belongs to the limit superior, then this implies that x belongs to E n for an infinitely many values of n. Now, once again, if x belongs to infinitely many values of n, then no matter for which value of m you start with, x will belong to certain sets after that, and therefore, this statement implies this. Now, since this is true for every m, this statement implies that x belongs to intersection union of E n's. This proves the statement 2. Further, we consider certain particular kind of sets, certain particular type of sequences where the limits will always exist. They are called monotone sequences. So, we say that a sequence E n is said to be monotonic increasing if E n is a subset of E n plus 1 for n is equal to 1, 2 and so on. In a similar way, we define E n to be monotonic decreasing if E n is a containing E n plus 1 for n is equal to 1, 2 and so on. Let us consider some example here. Let E n be the interval say 0 to 1 by n, then E n is monotonically decreasing sequence. Further, we can consider the say sequence E n is equal to interval say minus n to n, then E n is monotonically increasing. One important result which is true for the monotonic sequences is that the limit always exists. I will state it in the form of a theorem here. If E n is monotonically increasing, then limit of E n is equal to union of E n, n is equal to 1 to infinity. In a similar way, if E n is monotonically decreasing, then limit of E n is the intersection of the sequence of sets E n. To look at the proof, let me prove the statement 1 first. If we take the E n to be monotonically increasing sequence of sets, then the union En will be same for all m, and therefore limit superior will be same. Let me explain it further. If we consider limit superior of En, then it is equal to intersection union En, n is equal to m to infinity, m is equal to 1 to infinity. This will be equal to simply union n is equal to 1 to infinity, since union En n is equal to m to infinity will be the same for all m, as En is subset of En plus 1 for all n. Further, if we look at limit inferior of the sequence, then this is union intersection En, n is equal to m to infinity. Now, in the intersection En, this is starting from Em plus 1 intersection Em plus 2, etc. Since the sequence is monotonically increasing, the first set in this sequence is the smallest set, and it is contained in all the sets which are coming after this. Therefore, the intersection will be equal to the first set itself, and therefore, it is equal to Em. That means, we are getting limit infimum as also union of Ems. If we combine these two results, the limit exists and it is equal to the union of the sets. The proof of the second statement can be given by direct argument, as in 1, or we can use De Morgan's laws. Let me state as exercises a few more results which are related to the limit of the sequence of the sets. For example, if I consider limit superior of a sequence of sets, and if I take complementation of that, then it is equal to limit inferior of the complements of the sets. In a similar way, if I consider limit inferior of the sequence of sets and I take its complement, then it will be equal to the limit superior of the complements of the sets. The proofs will be almost trivial if we make use of the lemma 1, which gave the representation of the limit superior and limit inferior, and make use of the De Morgan's laws. An extension of this exercise would be, if I consider f minus limit infimum of the sequence En, then it is equal to limit superior of f minus En. In a similar way, if I consider f minus limit superior of En, that is equal to prove, say, the first part of this, we can consider f minus limit inferior of En, and let us write down the representation of the limit inferior in terms of unions and intersections. n is equal to m to infinity, m is equal to 1 to infinity. And at this we just use a set theoretic notation where a minus b is equal to a intersection b complement. So, this becomes f intersection union intersection E n, n is equal to m to infinity, m is equal to 1 to infinity complement. That is equal to f intersection union E n complement if we apply De Morgan's laws. Now, at this stage we can apply the distributive properties of the unions and intersections, and this will give us intersection m is equal to 1 to infinity union n is equal to m to infinity f intersection E n complement, which is equal to intersection union f minus E n, where n is equal to m to infinity, m is equal to 1 to infinity, and this is nothing but the limit superior of the sequence f minus E n. In a similar way, we can prove the statement 2 of this. There are certain relations which include the characteristic functions of the limit superior and limit inferior, and I will state it as a statement in the following exercise. Indicator function of the limit inferior of a sequence of sets is the limit infimum of the indicator functions of the sequence of the sets. In a similar way, if we consider indicator function of the limit superior, then it is equal to limit superior of the sequence of the sets we may look at the proof of say one of them. Consider say x belonging to E star, then this implies that x belongs to E n for all but finitely many values of n. This implies that the indicator function of the set E n is 1 for all but finitely many values of n, which is equivalent to the statement that limit infimum of the indicator function chi E n x is equal to 1, and these statements are both if and only if. Further, if I consider x not belonging to E lower star, then this will imply that x does not belong to E n for infinitely many values and this implies that limit infimum of chi E n x is 0. In a similar way, if we use the definition of the limit superior of a sequence of functions, then we will be able to prove the second statement. A useful relation which is used for in set theory is that of symmetric differences. The concept of symmetric difference is defined by A delta B is equal to A minus B union B minus A, So, you can see here that it is A minus B and B minus A both are combined together, and that is why it is called a symmetric difference. And an equivalent interpretation for this is A union B minus A intersection B. From the Venn diagrams, we can see that if I have two sets A and B, then the symmetric difference is the shaded portion. Certain relationships which are true for set theoretic operations are given in the form of exercises below. Prove that E minus F is equal to E minus E intersection F. It is equal to E union F minus F. E intersection F minus G is equal to E intersection F minus E intersection G. E union F minus G is equal to E minus G union F minus G. E minus G intersection F minus G is equal to E intersection F minus G. E minus F minus G is equal to E minus F union E intersection G. E minus F minus G is equal to E minus F union E intersection G. E minus F intersection G minus H is equal to E intersection G minus F union H. Certain relationships which are true for the symmetric differences are given in the next exercise. For example, symmetric difference of E with F is same as symmetric difference of F with E. Symmetric difference satisfies associative property, that is E delta F delta G is same as E delta F delta G. E intersection F delta G, it is equal to E intersection F delta E intersection G. That means intersection and symmetric differences are distributive. If we consider the symmetric difference of a set with the empty set, then we get the same set. That means as a group theoretic operation, empty set acts as an identity operator. If we consider with the full space, then I get the complementation. If we consider with itself, then we get empty set. That means with respect to group theoretic operation, E is its own inverse. And if we consider E delta E complement, then I get the full space. So, one can ask that the class of all subsets of omega forms an abelian group with respect to symmetric difference operation. Further, if we consider the indicator function of the symmetric difference, then it is equal to the absolute difference between the indicator functions of the two sets. An alternative way of telling it is that it is equal to chi e plus chi f, where the sum is taken modulo 2. An additional exercise in this direction can be that if we consider A, B, C and D then A delta B is equal to C delta D if and only if A delta C is equal to B delta D. In order to prove this statement 5, we proceed as follows. We show that either equality is equivalent to the statement that every point of x is in 0, 2 or 4 of the sets A, B, C, D. So, let us consider x to be any point in the space omega. Then there are 5 possibilities. Let us consider these possibilities. One possibility is that x belongs to none of the sets. If x does not belong to any of the sets, then with respect to this point A delta B and C delta D, they must be equal because x is none of them. If we consider x belongs to exactly one of sets, say x belongs to A, in that case A delta B will consist of the point x and C delta D will not include this point. If we consider x belonging to any two sets, let us take x belongs to A and x belongs to B, then clearly x does not belong to A delta B because the points which are common to both are excluded from the symmetric difference, and x does not belong to C delta D. So, A delta B will be equal to C delta D. Let x belongs to A and x belongs to D, then x will belong to A delta B and x will belong to C delta D. Let us consider the possibilities that x belong to any 3 sets, say A, B and C, then x will not belong to A delta B and x will belong to C delta D. If we consider x belongs to all 4 sets, then clearly x does not belong to A delta B and x does not belong to C delta D. Thus, we have proved that every point of x is in 0, 2 or 4 of the sets A, B, C, D implies statement 1. Similar statement holds for B. Hence, A and B must be equivalent. To end this class, we look at one or two more examples of the limit infimum, limit supremum, and let E n be equal to 0 to 1 minus 1 by n semi open interval if n is odd, and it is equal to 1 by n to 1 if n is even. Then if we look at limit inferior, it is the open interval 0 to 1. If we consider any real number between 0 to 1, then we can always find a capital N such that the point A will belong to both 0 to 1 minus 1 by n and 1 by n to 1 for all n greater than or equal to capital N. Therefore, the point will certainly belong to the limit inferior set. Since it will belong to limit inferior, it will also belong to the limit superior, and limit superior cannot be bigger than the interval 0, 1. Therefore, it is also equal to limit superior, and therefore, the limit of the sequence exists, and it is the open interval 0 to 1. Let me complete today's lecture by giving the final exercise. Let us consider a sequence of defined by that d1 is equal to E1, d2 is equal to d1 delta E2. In general, dn is equal to dn minus 1 delta En for n is equal to 2, 3 and so on. Show that the limit of the sequence dn exists if and only if limit of the sequence En is equal to 5. In next class, we will introduce the concepts of certain algebraic structures such as rings, sigma rings, fields and sigma fields, which are eventually going to be used for the definition of a probability function. Thank you.